Hello and welcome to 8.8 Improper Integrals. Improper integrals, these are definite integrals that are not, that are infinite, or integrals in which the function being integrated is not continuous on the integral. It's like might be discontinuous, have a broken part. Okay, so definition of improper integrals with infinite integration limits. If f is continuous in the interval from a to infinity, then the integral from a to infinity of f of x dx, this is what you do. You take the limit as b goes to infinity and integrate from a to b of f of x dx. And if f is continuous on the interval from negative infinity to b, then negative infinity to b of f of x dx is the limit as a approaches negative infinity from a to b of f of x dx. So we call it a usually for the lower limit, b for the upper limit. If f is continuous on the interval from negative infinity to infinity, then the integral from negative infinity to infinity of f of x dx is negative infinity to c f of x dx plus c to infinity of f of x dx. So this one here, you're going to say limit as a goes to negative infinity. This one here, limit as b goes to infinity. The first two cases, the improper integral converges if the limit exists, otherwise the improper integral diverges. The third case, the improper integral on the left diverges if either of these will diverge. Okay, example one, let me scroll this up a little bit. Or a lot bit. Determine whether the improper integral converges or diverges. Evaluate it if it converges. So we'll take the limit as b goes to infinity, integral from 1 to b of 1 over x squared dx. And as we know this is the limit as b goes to infinity. We know that it's going to become negative 1 over x from 1 to b. So we have the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. So that's going to be the limit as b goes to infinity of negative 1 over b plus 1. That's negative 1 over infinity plus 1. That's 0 plus 1 is 1. And that's it. So this converges to 1. So just because we have an infinite limit of integration does not mean that it's going to be an infinite result. Okay. Let me move this next one up a little bit. Determine whether the improper integral converges or diverges. Evaluate it if it converges. So we have the integral from 0 to infinity of x e to the negative x squared over, x over 2, not x squared, dx. Let's do this integration by parts, because I know this x will go away, the e will not. So we're going to say the limit as b goes to infinity, integral from 0 to b of x e to the negative x over 2 dx. So we'll say our u equals x, and we have x, 1, and 0. Our dv equals e to the negative x over 2, so we're integrating these. So we have e to the negative x over 2. Then we have negative 2e to the negative x over 2. And then we have 4e to the negative x over 2. I'm doing the antiderivative every time. And that one, it's plus minus plus. So we have the limit as b goes to infinity of x times negative 2e to the negative x over 2 minus 1 times 4e to the negative x over 2 from 0 to b. So we have the limit as b goes to infinity of negative 2b e to the negative b over 2 minus 4e to the negative b over 2 minus 0, negative 2 times 0 e to the negative 0 over 2 minus 4e to the negative 0 over 2. And I'll do this as a bracket. So we have the limit as b goes to infinity. Let me write this in a little bit different way. Negative 2b over e to the negative, e to the b over 2 minus 4 over e to the b over 2 and we have minus, what do we have over here? 2 times 0 is 0. So minus a negative makes it plus 4e to the 0 power. And this part's not really affected by that b. It's not affected at all. So watch this. I got to use L'Hopital's. Well, maybe I should back it up a little bit. So I have the limit as b goes to infinity of negative 2b over e to the b over 2. And then we have minus 4 over infinity by applying the infinity, b going to infinity, putting that in here, 4 over infinity, that's just 0, plus 4. So this part, we know this is going to go to 0, and this is indeterminate. So we'll do L'Hopital's rule. Limit as b goes to infinity, the derivative of negative 2b with respect to b is negative 2, and the derivative of e to the b over 2 with respect to b is 1/2 e to the b over 2. Now, plug in the infinity, it's negative 2 over 1/2 e to the infinity over 2. That's negative 2 over 1/2 infinity. That's just 0. So the result is 4. 0 plus 0 plus 4. So it converges. And let me change colors here. This 4 is the final answer. Okay. That was kind of fun. Improper integrals. Hey, we get to use L'Hopital's rule. That is a good thing here. So we're going to go on to the next page. So feel free to pause if you'd like to. That's good enough. We can see that. Try to get these both examples in one shot. Okay, so now we're going to take the limit as b goes to infinity, integral from 1 to b, natural log of x over x dx. So if I say u equals natural log of x, and du would be 1 over x dx, we're going to have the limit as b goes to infinity of integral of natural log of b over natural log of 1, we know that's 0 though, of, that's just a u du. So that becomes the limit as b goes to infinity of u squared over 2 from 0 to natural log of b. So we have natural log of b squared over 2 minus 0 squared over 2. So that's going to be the limit as b goes to infinity of 2 times natural log of b. No, I take it back. No. It is the natural log part of the squared, not the b. Minus 0. So now if you apply the infinity, we have the natural log of infinity gets to be squared over 2 minus 0, which is infinity. So this diverges. That's our first diverging of this section. Okay. Go on to example 4. Determine whether the improper integral converges or diverges. Evaluated for convergence. I'm going to scoot this up just a tad. Give us a little more space on the board. Okay. Determine whether the improper integral converges or diverges. Okay, so we have the limit as b goes to infinity, integral from 0 to b of e to the x over 1 plus e to the x dx. So if I say my u is 1 plus e to the x, my du would just be e to the x dx, and I'll have the limit as b goes to infinity of the integral. Now 1 plus e to the 0 is 1 plus 1, which is 2. And we'll have 1 plus e to the b up here. And we have 1 over u du. That's going to give us natural log of the absolute value of u. I don't need absolute values because I'm dealing with positive values here. From 2 to 1 plus e to the b. So we have the limit as b goes to infinity of the natural log of 1 plus e to the b minus natural log of 2 so we're looking at natural log of 1 plus e to the infinity minus natural log of 2. This part here is infinity. So we have infinity minus 2, which is infinity. So it diverges. Okay. So we had 2 converge, 2 diverge. We're batting about 50 or 500 as they say in baseball. Okay, moving on here. We've got some definitions. Clear the board. Okay, definition of improper integrals with infinite discontinuities. If f is continuous on the interval from a to b and has an infinite discontinuity at b, then the integral from a to b of f of x dx is the limit as c approaches b from the left side, from a to c of f of x dx. So if it's discontinuous at b, so it goes up to be infinitely close to b but never at b, so always on the left side. If it's discontinuous at a, then we can do the limit as c approaches a from the right side from c to b. So if it's discontinuous in some place in the middle, and there's a typo here, except for some c, the interval on AB. So if it's discontinuous at c, you can do the integral from a to b of f of x dx is a to c of f of x dx plus c to b of f of x dx. You can split your interval up. The first 2 cases, the improper integral converges if the limit exists. Otherwise, the improper integral diverges. Third case, the improper integral will converge if they both converge, but it'll diverge if only one of them diverges. And there's a typo here that should say an A. So it says approaches A, or has discontinuity at A. Okay, so evaluate the limit, or determine whether the improper interval diverges or converges. Now it's 1 over x squared, and we have a 0 down here. So 0 in the denominator is going to be a problem, so we'll do that as our limit. So limit as c approaches 0 from the right side, integral from c to 1 of 1 over x squared dx. It's going to be the limit as c approaches 0 from the right side of negative 1 over x from c to 1. That's the limit as c approaches 0 from the right side of negative 1 over 1 minus negative 1 over c. So that's the limit as c approaches 0 from the right side of 1 minus, or 1 plus 1 over c, negative 1 plus 1 over c. So that's going to be negative 1 plus 1 over 0, which is negative 1 plus infinity, which is infinity. So it diverges. Okay, so for number 6, determine whether the improper integral diverges or converges. Evaluate the integral if it converges. So here, we can't take natural log of a 0. That's a problem. So we'll say the limit as c approaches 0 from the right side again, integral from c to e, natural log of x squared dx. Limit as c approaches 0 from the right side of 2 times the power here can come out front, integral from c to e, natural log of x dx, and we'll use formula 87. That's going to give us the limit as c approaches 0 from the right side of 2 times x times negative 1 plus natural log of x from c to e. So we're going to have the limit as c approaches 0 from the right side of 2e times negative 1 plus natural log of e minus 2c times negative 1 plus natural log of c. That's going to give us the limit. Well, I think I can pull this part out of the limit now because there's no c in there. So we're going to have 2e times negative 1 plus 1, because natural log of e is just 1. Minus, here, 2 times 0 times negative 1 plus natural log of 0. Now the problem with natural log of 0, that is going to be negative infinity. So we have a 0 times negative infinity case. So here we're going to have to use L'Hopital's rule. Okay. So we'll do our limit as c approaches 0 from the positive side of negative 2 times c times negative 1 plus natural log of c. So be the limit as c goes to 0 from the right side of negative 1 plus natural log of c over, I should put that 2, I'll just pull the 2 out, negative 2 here, over 1 over c. There we go. Oh, there's a double, no? Is there a double negative issue? Okay, we're good. Now, applying L'Hopital's rule, we have -2 times the limit as c goes to 0 from the right side of the derivative of natural log of c is 1 over c. The derivative of 1 over c is -1 over c squared. So if you flip that around, that's -2 times the limit as c goes to 0 of -c squared over c. It's -2 limit as c goes to 0 of -c. So that's going to be -2 times 0, which is 0. So surprisingly, this one converged. So this converges to 0. So I'm going to step over here. Feel free to pause it if you'd like to pause it. Take some time to write that down. Of course, there are always the notes you can print off. They're a little different, but they're close. And moving on to example 7. Says determine whether the improper integral diverges or converges. Evaluate the integral if it converges. So here we have 1 over the cube root of x minus 1. Well, x minus 1, as this function sits, 1 minus 1 is 0. 1 is in the range here from 0 to 2. So we'll break this out to be the integral from 0 to 1 of 1 over the cube root of x minus 1 dx plus integral from 1 to 2 1 over the cube root of x minus 1 dx. So we'll take the limit as I'm going to do b, as b approaches 1 from the left side of the integral from 0 to b of 1 over the cube root of x minus 1 dx plus the limit as a approaches 1 from the right side integral from 1 to 2 of 1 over the square root of cube root of x minus 1 dx. In the notes I did just the opposite. I said this was the a and this is b. So let's see. We have the limit as b approaches 1 from the left side of what? So if we integrate that, that's like x minus 1 to the negative 1/3. That becomes x minus 1 to the 2/3 divided by 2/3 from 0 to b. Plus limit as a approaches 1 from the right side. Maybe those pluses on the wrong side. There. There and there. Okay. Of x minus 1 to the 2/3 over 2/3 from a to 2. So let's keep going. Limit as b approaches 1 from the left side of b minus 1. I got the 2/3 there, so I'm going to pull the 3/2 out. B minus 1 to the 2/3 minus 0 minus 1 to the 2/3. Plus limit as a approaches 1 from the right side of 2 minus 1 to the 2/3 minus a minus 1 to the 2/3. Okay, so we have And I didn't pull the 3/2 out there either. So 3/2 out here times all this stuff. I can put the 1 in there. We have 1 minus 1 to the 2/3 minus negative 1 to the 2/3 plus 2 minus 1 is 1 to the 2/3 minus 1 minus 1 to the 2/3. So it's 3/2 of 0 minus, now this is what? Minus negative 1, cube root of that's negative 1, squared is 1. So that's negative 1 plus 1, and that part's 0. So it's 3/2 of 0, which is 3/2. No, it's 0. So it converges to 0. That's it. But we had to split that up because this original function was discontinuous at 1. So we had to split that up. Okay. Ready to go on to the last page for our last two problems here. Feel free to pause that if you'd like. Okay, says theorem 8.5, a special type of improper integral. Integral from 1 to infinity of dx over x to the p is equal to 1 over p minus 1 if p is greater than 1. But it diverges if p is less than 1. If p is less than 1, you're going to have the integral to be something greater than, it essentially be like, let's say p is 0.5. You have 1 over x to the 0.5, or x to the negative 0.5, integrate that, you get x to the 0.5. If you plug in infinity, you're going to have infinity. But if you have like a 2 down here, if you integrate that, you're going to have negative 1 over x. So you put an infinity in there, you're going to have 1 over infinity, you get 0. Okay, determine all the values of p for which the improper integral converges. So this is a little different now. This was from 1 to infinity, this is from 0 to 1. So we'll take the limit as a approaches 0 from the right side of the integral from a to 1 of 1 over x to the p dx. When we integrate that, we'll have the limit as a approaches 0 from the right side of x to the negative p plus 1, because think of this as x to the negative p plus 1 over negative p plus 1 from a to 1. And that would be 1 to the negative p plus 1 over negative p plus 1 minus a to the negative p plus 1 over negative p plus 1. So if we take the limit as a approaches 0 from the right side of, we have 1 over, basically 1 minus p minus a to the negative of p minus 1, so just factor the negative out, over 1 minus p. So this is the limit as a approaches 0 from the right side of, same denominator so we can combine the numerators. Actually, before I do that, I'm not going to do that. I'm going to bring this down. 1 over 1 minus p minus 1 over a to the p minus 1 times 1 minus p. Now if I plug in 0 for a, I'd have 1 over 1 minus p minus 1 over 0 times 1 minus p. That's 0 to the p minus 1 times 1 minus p. Okay. So p check this out, this is down below. P minus 1, I should write it down here. P minus 1 is negative. If this power is negative, that 0 is up top. This power is positive, it's down here. So to make that negative, P would have to be less than 1. P minus 1 is greater than 0 if P is greater than 1. So if P is less than 1, see right there, this converges to 1 over 1 minus P, because your 0 would be in the numerator in that case. If P is less than 1, no, greater than 1, this diverges. Okay, and it fails at P equals 1. Because you have a 0 to the 0 power, so it fails. You have to use L'Hopital's rule. So in the second case, here, that'd be like 1 over 1 minus P minus 1 over 0 times 1 minus P, which is 1 over 1 minus P minus 1 over 0, and this diverges. That's for the case where P is bigger than 1. Okay, and that's it. So we're going to use this result in example 9. Determine whether the improper integral converges or diverges. So from example 8, if P is greater than 1, it converges. Well, in this case, P equals 3, which is greater than 1, so this converges. That's it. Oh, I got that backwards. P is less than 1, it converges. P is greater than 1, so this diverges. Oh, got that backwards. Diverges. Sorry about that. So this diverges. And that'll do it for 8.8. That'll do it for chapter 8, in fact. Okay, so send me your questions, and I'll see you guys online. Thanks.